Hi, my name is Daniel Bozing, and this is my application to create content for boiler exams. As an IE at Purdue, I've taken all the way from pre-calc to Diff-EQ. I've also applied many of those mathematical concepts in a multitude of engineering courses. As far as teaching others content, I've worked with many clients as a math tutor at Purdue for several months. Every math problem can be broken down into lower levels of abstraction. I believe it is necessary to guide students down each level of specific detail until they understand the problem. Strategies I use for this are effective visuals, highlighting keywords and problems indicative of the necessary steps, and providing step-by-step flowcharts to show the whole problem-solving process. So I'm going to show you how to solve geometric optimization problems, and for this problem we've got a 40 by 30 rectangular piece of cardboard with the corners removed, and we want to know what height will give us the highest possible volume. So you got to ask yourself what you're trying to find, and that's the height of the box that will maximize the volume. And from there, what do you know about that? And we know the volume of a box is length times width times height. Then you ask the question, is there a way to visualize it? And this one is a very easy one to visualize, as can be seen in the illustration here. So the problem statement gives us some information, but not all of it. So a question we need to ask is, what other information do we need to solve this problem? And we need to know the height, because with the 40 and 30, from there we can deduce the length and the width, but we need to find a way to relate. So the problem statement gives us some. So as you can see in the video, the dimension that is responsible for height in 2D is the dimension of the square corner you're cutting off. So a common mistake to watch out for that I see a lot of students make is they want to say, oh, we're given that it's 40 inches long and 30 inches wide, so that's our length and width. And they'll put that as the length and width and the volume formula for the box. However, you're going to have to remember that the corners are being cut off, so because of that, we're going to have to update our dimensions. Okay, so we know we can't use the 30 and the 40, but how can we relate this information to solving the problem? Well, we showed that x determines the height, so from there you can see when you cut off a corner, your length is going to become 40 minus 2x and width is 30 minus 2x, and you can use that information to update the equation for volume. Okay, so now that we have our volume formula relating to height, which in our case is x, how do we determine what that x value or height is going to give us the maximum volume? Well, according to the critical number theorem, a function's critical points are the zeros of its derivative. And critical points are where a function has a relative maximum, minimum, or saddle point. And maximum or minimum is what we're mainly going to be looking at in an optimization problem. So if we want to be able to find the height that's going to be able to maximize our volume, we're going to want to use this theorem. So the first step to using this theorem is to take the derivative of the volume function. And I think it's a lot easier to derive this if you simplify it first. So see, you can simplify it out to a really clean looking polynomial, and from there you can just use the power rule and get the derivative down at the bottom. So now that we've taken the derivative of the volume, we got to find the zeros. And to do that, we're going to use the quadratic formula. So once you plug in your a and b and c, your zeros come out to be 17.676 and 5.657. Now, a common mistake I see a lot of students make is they think finding the critical points is the end of the problem since they've done their calculus, right? However, we're wanting to find the maximum, right? So one of these is going to yield a higher volume than the other. So you have to compare those two. And I'm going to do that by plugging it into the volume equation. However, you can also do it with the second derivative test. So now that we have our critical points, we're going to compare them by plugging it into the volume. So the 17.676 gives us a negative volume, and we know that can't be right, so it has to be the other one. And whenever you plug in that 5.657, that's going to give you your maximum volume of 3,032.302 cubic inches, and then you're done solving the problem. And then an easy way to check our work is to plug our volume equation into Desmos and see if it gets the same maximum, and it does. So now that we've solved the problem, I want to show a thought process that you can do for these similar types. And so here, where he's got a new problem, I'm going to show you how to interpret it, right? So we got a cylindrical can with a bottom and no top with a given volume. So that's going to show you can visualize it like a can with its top cut off. Then with this phrase, the determine dimensions of the can, that shows it wants all the variables, so you don't know any of them. And then minimize should be sirens in your head saying we're going to use the critical number theorem because it's optimization. And then the amount of material to construct the can, that shows you that it's a surface area. So So here's a process you can go through to solve any of these types of problems. So first thing to do is write out the formulas. So in our case, we've got volume and surface area, and then you're going to see if you need to modify anything in the formula. In this case, yes, the top's cut off, so that's going to affect it, and then we also want it in terms of a variable. So we're going to simplify it to put it all down in front of the terms of r. From there, you're going to take the derivative of that function, and then once you have that derivative, find the zeros, and from there, plug it into the original, and you get your answer.